Hi, I'm Yogesh. I'll present our work on randomized versus deterministic decision tree size. This is joint work with Arkadev Chattopadhyay at TIFR Mumbai, Nikhil Mande at CWI Amsterdam, Jaikumar Radhakrishnan at ICTS and TIFR, and Swagato Sanyal at IIT Kharagpur. So let me start by telling you about the problem setup. So we are given a Boolean function, and we would like to find out a succinct representation of that function using decision trees, where a decision tree is a rooted binary tree whose internal nodes are labeled by variables and whose leaves are labeled by 0, 1. An evaluation on decision tree is done as follows. On an input x, we start from the root node and traverse down to a leaf node, querying variables one by one. And if a variable evaluates to a 0, we go left. And if a variable evaluates to a 1, we go right. And finally, we return the label of the leaf node. As you can see, the evaluations of a decision tree naturally induces some Boolean function. And we say that a decision tree computes a function f if for every input x, the evaluation of a decision tree is same as the function value. Okay. Now, for every Boolean function, there is a trivial decision tree which queries all the variables one by one. And for such a tree, one can see that the leaves corresponds to all the possible 2 to the n inputs. So one can place the truth table of a function on these leaves and can compute any function using this trivial decision tree. Okay. So for every function, we have this trivial decision tree, and now the goal is to find out a succinct representation, a succinct decision tree which computes our function. Okay. How do we measure succinctness in case of decision tree? The two complexity measures which are studied in literature are this depth and the size measure for decision tree, where a depth of a decision tree is the length of the longest root to leaf path, and the size of the decision tree is the number of leaves in it. Okay. Now one can define complexity of a Boolean function using decision trees. For example, one can define deterministic depth complexity for function as decision tree depth complexity of function as minimum depth among all decision tree which computes f. And similarly, one can define deterministic size complexity of Boolean function f as minimum size among all decision trees which compute f. Let's see some examples. On left, we have a parity function which calculates parity of n bits. And the decision tree for parity function is a trivial decision tree, because one can argue that in case of parity, nothing clever could be done. And so the depth complexity of parity function is n, and its size complexity is 2 to the n. On the right, we have an AND function, which calculates logical AND of n bits. And the decision tree for AND function queries all variables one by one. And if at any points if at any points a variable evaluates to a 0, it outputs a 0. Otherwise, it outputs a 1 after verifying that all the variables are equal to 1. Okay, and one can check that this decision tree is optimal for AND function both in terms of size and in terms of depth. And so the depth complexity of AND function is n, and size complexity is just n plus 1 because of this lopsided nature of AND function. Now, the decision trees that we have defined so far, we'll call them deterministic decision trees because there is no notion of randomness in them. And we'll introduce the notion of randomness by defining randomized decision trees. So a randomized decision tree is nothing but a distribution over deterministic decision trees. And the evaluation on randomized decision tree is done as follows. On an input x, we sample a decision tree. We sample a deterministic decision tree from our underlying distribution and output the value of input on that decision tree. Okay. And we say that the randomized decision tree computes f with error epsilon if for every input x, the probability of randomized decision tree outputting the correct answer is at least 1 minus epsilon. Okay. So epsilon here is the error parameter, and we'll assume it to be 1/3 whenever it is not specified. The depth of a randomized decision tree is the maximum depth among all decision tree in its support. And similarly, the size of a randomized decision tree is maximum size among all decision trees in its support. Now, similar to deterministic case, again, we can define complexity of a Boolean function using randomized decision trees. Okay. For example, epsilon error randomized depth complexity of Boolean function f is the minimum depth among all randomized decision trees, which computes f with error epsilon. Okay. And similarly, epsilon error randomized size complexity for Boolean function f is the minimum size among all randomized decision trees, which computes f with error epsilon. Now, having defined complexity of a Boolean function using deterministic decision trees and randomized decision trees, one can ask how these complexities are related. Okay, so one can ask what is the relationship between randomized depth and the deterministic depth, and similarly, one can ask what is the relationship between randomized size and the deterministic size. The answer to the first question was given in the celebrated work of Nissan in SciComp 91, where he showed that the deterministic depth and the randomized depth are cubically related. Okay. And very recently, Ambani's, Bellows, Lee, Santa, and Montrose showed that the deterministic depth and the randomized depth are at least quadratically separated. Okay. And the exact relationship between deterministic depth and the randomized depth is still an open problem. That is, we don't know whether 3 in the Nissan result is optimal or not. We know that it should be somewhere between 2 and 3, but the exact relationship is still unknown. So let me say more on how Nissan showed his result, because it will be instructive for us later on. What Nissan did was he introduced this beautiful combinatorial notion called block sensitivity and characterized both deterministic depth and the randomized depth of a Boolean function using block sensitivity. And that's how we ended up relating deterministic depth and the randomized depth. So let me introduce this notion of block sensitivity. And before that, I'll need a notion of sensitive block. A subset B of 1 to the n, we say is a sensitive block for f at input x if the value of function at input x and the value of function at input x with bits in B flipped are different. Okay, such a block is known as sensitive block at that input. For example, in our slides, we have an input and the function evaluates to 0 on that input. And when we flip the second and fifth bit, the function value changes. And so the 2 and 5 forms a sensitive block for f at this given input. So block sensitivity of a function at input x is the maximum k such that there exists k disjoint sensitive block for f at input x. So disjoint is important here. And the block sensitivity of a function is just maximum overall inputs. Let's see some examples. Block sensitivity of AND function is n, because on all one input, every one bit is sensitive. Okay. And similarly, one can check the block sensitivity of a majority function is n by 2. So let me say how Nissan proved his result. So what Nissan showed was, he showed that this block sensitivity is a lower bound on the randomized depth complexity. And the deterministic depth complexity can be upper bounded by block sensitivity to the power 3. And that's how he related both randomized depth and the deterministic depth. Okay. What about size? Can we show similar relationship between deterministic size and the randomized size? Can we show a polynomial relationship? Even let's say we allow poly-n factors. Can we show such relationship? And as it turns out, the answer to this question is no, because there exists a function based on AND or tree, where this function is represented by a monotone formula of depth log n with binary AND and OR gates in alternating layers. And for this function, it was shown by Snare that the deterministic size is 2 to the omega n. And from the work of Sachs and Wigderson, one can imply that the randomized size for this function is 2 to the order n to the 0.75. So as we can see, for this function, we already have an exponential separation between d size and r size. So there is no hope of proving this polynomial relationship. But if we look closely, it seems that on the log scale, the gap is still polynomial. Okay? And so one can ask whether log of deterministic size and log of randomized size are polynomially related. And up to polylog factor, this question is exactly same as a very recent conjecture by Cornelian, Mande, and Patro in FSTTCS 22. And indeed, this is the case, and this is our main theorem of our paper. We show that log of deterministic size is indeed polynomially related to log of randomized size. So what this tells us is that if the deterministic size is large, then the randomized size cannot be too small. For example, if the deterministic size is exponential, then the randomized size cannot be just polynomial. Okay. So the proof of this theorem is very much inspired by Nissan's result, because what we do is we also look for combinatorial notions which can characterize both log of deterministic size and log of randomized size. Okay, I'll say more on this, but let me introduce this combinatorial notion, which will be crucial in proving this result. So the one notion we'll need is this notion of block number. So we already saw the notion of sensitive block. So now we define notion of minimal sensitive block. So a block is minimally sensitive for f at input x if that block is sensitive, and moreover, no proper subset of that block is sensitive for f at input x. And the block number of f at input x is just number of all minimal sensitive block for f at input x. Okay, and the block number of function is just maximum over all inputs. And as it turns out, this notion of block number will be very crucial in proving our result. Okay. And this notion has also appeared in earlier work of Midrianis and later on in work of Kulkarni and Tal in a different context. So it seems it's a very interesting and useful measure. Let's see some examples. So for parity function, no matter what the input is, one can see that every set of odd bits form a sensitive block. Okay, but the minimal sensitive blocks are these single bit blocks. Okay, so that's why the block number of parity function is just n. Okay, for majority function, one can see that on all zero input, every set of n by 2 bits forms a minimal sensitive block. And so the block number is at least n choose n by 2. And since this is the maximum possible value of a block number, it is exactly n choose n by 2. Okay. So the other important notion, which is important in our work, is this notion of cover number. And to define it, I'll need the definition of subcube. So I'll define it. So subcube of codimension k is a subset of 0, 1 to the n obtained by fixing k variables. Okay. So it's nothing but a set of all inputs which are consistent with a partial assignment. Okay. And we say a subcube is monochromatic with respect to a Boolean function f if for every input x, the value of the function is same. Okay. Now we define the cover number. So the cover number for a function f is the smallest k such that there exist k monochromatic subcubes with respect to f, which span the whole space, which covers the whole space. Okay. This cover number is sometimes also referred to as non-deterministic size of a Boolean function. And a very easy proposition that one can check is that that the cover number provides a lower bound on the deterministic size. Because given any function, any decision tree which computes a function, the leaves of the decision tree, all the inputs which reach a leaf node, one can see they form a monochromatic subcube. Okay? So the subcube corresponding to these leaf nodes will end up giving a partitioning of the whole space. So that's why the cover number is upper bounded by deterministic size. In the other direction, there is this result of Aaron Faust and Hausler, which showed that if the cover number is small, then the log of deterministic size is also small. So there is a quadratic relation between log of cover number and log of D size up to this log n factor. So what this tells us is that log cover number already characterizes log D size polynomially. Okay. So we already have a combinatorial notion which characterizes log of deterministic size. And if somehow we can relate this log cover number to the log of randomized size, then we will be able to relate log D size and log R size. And that's exactly what we do in our result. Okay. So in our result, we show that the log of cover number can be upper bounded by the product of log of randomized size and the log of block number. Okay. And then we show that if the randomized size is small, then the block number is small anyways. Okay. So then what this tells us is that if the randomized size is small, then the cover number is small. Okay. So this tells us that the cover number is upper bounded by log of randomized size to the power 2. And now combining this cover result with the result of Aaron Faust and Hausler, we get our size theorem. Okay. So let me say something about dilemma 2, which says that if the block number is large and the randomized size is large. Now, in the other direction, this does not hold. What I mean is that if the block number is small, then we cannot say that log randomized size is small, because we had this counter example. Parity is a counter example because for parity, the block number is n, but the randomized size for parity is 2 to the omega n. Okay. So the way we showed this result was to relate cover number with the randomized size. There are several consequences of our result in de-randomizing depth in more general decision trees. The two kind of decision tree that we study are these and/or decision trees and AND decision trees. The and/or decision trees are decision trees where the internal nodes are allowed to query AND of subset of variables and or of subset of variables. Okay. And again, one can ask, what role does randomness play in such decision trees? We show that the depth complexity, the deterministic depth complexity, and the randomized depth complexity in and/or decision tree is also polynomially related up to polylog factors. And this result is a direct consequence of our size theorem, because we observed that the depth in and/or decision tree is characterized by log of size in ordinary decision tree up to log n factor. Okay. And since we already have a relationship between deterministic size and the randomized size in ordinary decision trees, we instantly get this result. Okay, so it's a very direct consequence of the size theorem. We also study AND decision trees, where we only allow AND queries. There are no OR queries in them. And for such decision tree, again, one can ask, what is the role of randomness in such decision tree? And indeed, in a very recent survey by Knopp, Lovett, McGuire, and Yuan, it was conjectured that the randomized and deterministic depth complexity in AND decision trees are polynomially related. And we show that this is indeed the case, that the deterministic depth and the randomized depth in AND decision tree are cubically related. Okay. And we have to do slight more work for this result, because the log of ordinary size does not characterize depth in AND decision tree, as was the case in AND OR decision tree. So we needed a different route. And for a good reason, because the AND depth complexity of OR function in AND decision tree is n, and the ordinary size complexity for OR function is n plus 1. Okay, so there cannot be the ordinary size, the log of ordinary size cannot characterize depth in AND decision trees. So in interest of time, I'll not say more on this result, but it's very much in the spirit of Nissan's result. We tried to find out combinatorial notions which can characterize a deterministic depth and randomized depth in AND decision trees. And that's how we ended up relating these two quantities. Let me say something about the quality of our results. In both of our results, for AND OR trees and for AND trees, we have polylog factors in our relationship, and one can ask whether one can avoid these polylog factors. And as it turns out, that for these two theorems, some dependence on input must be there, because there is this counter example based on threshold function, for which the deterministic AND OR depth complexity is theta log n, and the randomized AND decision tree complexity is just order 1. Okay. So some dependence on input will come in these theorems. About the separation or the optimality of our size theorem, we observed, it was brought to our notice by Vikyang Yuan, that the separation between log D size and log R size is at least as large as the separation between deterministic depth and the randomized depth. This observation was told to us by Vikyang Yuan, and we thank Vikyang for this observation. And so the deterministic size, log of deterministic size and log of randomized size are at least quadratically separated, because deterministic depth and randomized depth are quadratically separated. And the same thing holds for AND decision trees. That is, the depth, deterministic depth and the randomized depth in AND decision tree is at least quadratically separated. And also, I mean, one can argue that this result of ours is a generalization of Nissan result, in a sense that we can recover Nissan's result, Nissan's cubic relation between deterministic depth and randomized depth can be recovered starting from this result up to polylog factors. So improving this relation, I mean, improving this 3 to something below 3 will improve Nissan's result, which is a long-standing open problem. Let me summarize our result. We established the log of deterministic size is polynomially related to log of randomized size. And en route to proving this theorem, we proved that the cover number provides a lower bound on randomized size. And using our size theorem, we de-randomized depth in AND OR decision trees and in AND decision trees. Okay. And that's all I have. Thanks for listening.